Hey guys, Mr. Hartz here. I just wanted to give you a better visual of what was going on in that day 88 video. So here we have two functions, f of x, g of x, bounding a region. As we can see here, it says the region is the base of a solid whose cross sections perpendicular to the x. Notice these cross sections, these ones are squares. Notice how they are perpendicular to the x-axis. Okay, so it looks something like this. Okay, so it's kind of a weird solid. Now, I put in, 7 pieces of paper, but really just imagine paper filling every possible gap. Notice how some of these squares are really little, and some of these squares are big. Okay, but this is just what it's looking like. Now, if you imagine removing one of those, so here's one that maybe went right here, okay? When I remove that, this distance here, this distance is a distance of top function minus bottom function, so f of x minus g of x, f minus g. And since it's a square, this bottom length is also f minus g. Okay? And notice, no matter whether it's one of the little squares by the edge or one of the bigger squares in the middle, right? This distance right here is always a distance f minus g. Since the shape happens to be a square, the height is also f minus g. So if I wanted to write an integral here, to solve this, I'd say the volume equals the integral from a to b. And then what I do is I just do the area of this shape. The area of that shape is f of x minus g of x squared. So I'm going to write that, f of x minus g of x squared. And then dx would be the thickness. As we can see, this piece of paper the thickness is very, very small, right? But there is some thickness. In actuality, it's infinitely thin, okay? But we have to put this in to make the volume. So this is area of shape, and then this is the thickness, okay? To get your volume. Now, what if we have different shapes? Well, one of the shapes that you'll see on your homework is a rectangle. And they say, I think in the problem, they say the rectangle is 5 times taller, right, than it is wide. Let me just show you on a different one here. Right, just imagine all of these rectangles. Right, and again, what is this distance here? Well, that is the f minus g. Or actually, notice I switched it. That is g minus f. It's always top minus bottom. Okay, what would this be then? Well, it's got to be 5 times bigger than that. So it'd be 5 times g minus f. Okay, so if I wanted to write this one, again, let's say this is A and this is B, my volume would be the integral from A to B, and then it's going to be, the area here is going to be 5g minus f times g minus f, which would equal 5 times g minus f squared. So when I write my integral, I can put the 5 out front, and then I can do g minus f, sorry, I'll use x's, g of x minus f of x squared. Again, that's my area. To get volume, then I need dx. Okay? And then the toughest one is semicircles. Okay, so here's a semicircle. Okay? So when I take the semicircle out, I know that this distance right here is g of x minus f of x. Okay? Now, the area of a semicircle is going to be half pi r squared. But what you have to see here is g minus f doesn't represent the radius. That represents the whole diameter. So to get my radius, I have to do half of g of x minus f of x. So this is going to look like half pi g of x minus f of x over 2 squared. So if I wrote my formula here, I would say volume equals, I'm going to take this half pi and put it out front, integral a to b, and then it would be g of x minus f of x over 2 squared dx. Okay? That's it for an addition. Hopefully that helped you visualize it a little bit better. Talk to you guys later. 2 chains. Bye.